Hello, space enthusiasts, and welcome back to our channel. Today, we're embarking on a journey to the heart of our solar system to uncover one of its most fascinating and mysterious phenomena: sunspots. Have you ever looked at images of the sun and noticed those strange, dark blemishes on its surface? They might look small from here, but these are colossal storms, some larger than our entire planet. What exactly are they? Why do they appear dark? And how do these solar freckles affect us here on Earth? Stick around, because we're about to dive deep into the fiery, turbulent world of sunspots. It's a story of intense magnetism, powerful eruptions, and a cosmic dance that has captivated scientists for centuries. So, let's start with the basics. What is a sunspot? In simple terms, a sunspot is a temporary dark spot on the sun's photosphere. That's the visible surface of the sun. But dark is a bit misleading. They aren't actually black holes or empty spaces. They're incredibly hot and bright, just like the rest of the sun. The reason they appear dark is purely by contrast. A typical sunspot has a temperature of around 3,500 degrees Celsius. While that sounds unimaginably hot, it's significantly cooler than the surrounding photosphere, which blazes at about 5,500 degrees Celsius. This temperature difference makes the sunspots look like dark patches against the blindingly bright backdrop of the sun. Think of it like a glowing ember next to a powerful searchlight. The ember is still bright, but it appears dim in comparison. Now for the multi-trillion-dollar question: what creates these cooler regions on an otherwise scorching hot star? The answer lies in magnetism. The sun is a gigantic ball of superheated electrically charged gas called plasma. This plasma is constantly in motion, churning and swirling, which generates incredibly powerful and complex magnetic fields. Sometimes, these magnetic field lines become twisted and concentrated in certain areas. They get so intense that they push up from the sun's interior and burst through the surface. When this happens, the magnetic pressure inhibits the flow of hot gas from below, essentially creating a plug that traps cooler plasma at the surface. This magnetic bottleneck is what we see as a sunspot. The darkest part in the center is called the umbra, where the magnetic field is strongest, and it's surrounded by a lighter region called the penumbra. One of the most intriguing things about sunspots is that they aren't random. They follow a predictable, albeit not perfectly regular cycle. This is known as the solar cycle, which lasts approximately 11 years. Over this period, the number of sunspots waxes and wanes. At the beginning of a cycle, a period called the solar minimum, there might be very few or even no sunspots at all. As the cycle progresses towards the solar maximum, the sun becomes peppered with more and more sunspots. Then, the activity gradually declines back to a minimum, and the cycle begins anew. What's even more fascinating is that with each new cycle, the sun's overall magnetic polarity flips. The north magnetic pole becomes the south, and vice versa. It's a grand cosmic reset that happens right on our cosmic doorstep every decade or so. Scientists track these cycles meticulously, because the level of solar activity has a direct impact on our planet. So how do these distant solar blemishes affect life on Earth? Well, the intense magnetic fields associated with sunspots are breeding grounds for some of the most violent events in the solar system: solar flares and coronal mass ejections, or CMEs. A solar flare is a sudden, intense burst of radiation, while a CME is a massive eruption of solar plasma and magnetic fields into space. When these eruptions are aimed at Earth, they can have significant consequences. This phenomenon is often referred to as space weather. On the beautiful side, these charged particles interact with our planet's magnetic field and atmosphere to create spectacular auroras, the northern and southern lights. The more active the sun, the more frequent and vibrant the auroras become, sometimes appearing at much lower latitudes than usual. It's nature's most incredible light show, powered by the sun. But space weather isn't all beautiful lights. It has a disruptive side too. The influx of energetic particles and radiation can pose a risk to astronauts and satellites in orbit. It can damage sensitive electronics, disrupt GPS signals, and interfere with radio communications. In extreme cases, a powerful solar storm can even induce electrical currents in power grids on the ground, potentially causing widespread blackouts. One of the most famous examples is the Carrington event of 1859, the most intense geomagnetic storm in recorded history. It caused telegraph systems worldwide to fail, and even set some telegraph offices on fire. If a storm of that magnitude were to hit our modern, technologically dependent society today, the impact could be far more severe. This is why agencies like NASA and NOAA constantly monitor the sun, tracking sunspots and watching for potential eruptions. Observing sunspots has a rich history. Long before we had satellites and advanced telescopes, ancient astronomers were noticing these dark spots. Chinese astronomers made the earliest known records of sunspots over 2,000 years ago, often observing them during sunrise or sunset when the sun's glare was reduced by the atmosphere. However, it was Galileo Galilei in the early 17th century who, using his newly developed telescope, made systematic observations. He tracked their movement across the sun's face, proving that the sun rotates on its axis. This was a revolutionary discovery that challenged the prevailing belief of a perfect, unchanging celestial realm. His work laid the foundation for modern solar physics and our understanding that the sun is a dynamic and ever-changing star. Imagine the courage it took to point a telescope at the sun and challenge centuries of established doctrine. Today, we have an incredible array of instruments dedicated to studying our star. Ground-based telescopes and space-based observatories like NASA's Solar Dynamics Observatory, SDO, and the Parker Solar Probe provide us with breathtakingly detailed high-definition views of the sun. The SDO, for example, captures an image of the sun every few seconds across multiple wavelengths of light, allowing scientists to see sunspots forming, evolving, and unleashing their energy in real time. The Parker Solar Probe is on an even more daring mission, flying closer to the sun than any spacecraft in history, literally touching the sun's atmosphere to sample its particles and magnetic fields. These missions are helping us unravel the complex physics behind sunspots and improve our ability to forecast space weather, protecting our technology and infrastructure from the sun's occasional fury. So, what have we learned? Sunspots are not just simple blemishes. They are windows into the sun's powerful and chaotic magnetic interior. They are cooler, magnetically intense regions that appear dark only by contrast. They follow an 11-year cycle of activity that directly influences our planet, creating both the beautiful spectacle of the auroras and the potential hazards of space weather. From ancient skygazers to Galileo's groundbreaking observations, and today's advanced space probes, our quest to understand these solar spots is a story of human curiosity and scientific progress. They remind us that we live in a dynamic solar system, connected to our star, in ways we are still just beginning to fully comprehend. The sun isn't just a distant, static ball of light. It's a living, breathing star with a temper, and its freckles tell its story. Thank you so much for joining me on this journey to the sun today. I hope you found it as fascinating as I do. If you enjoyed this video and want to explore more wonders of the cosmos with us, please hit that like button and don't forget to subscribe and ring the notification bell so you won't miss our next adventure. What cosmic topic should we explore next? Let me know in the comments below. Until next time, keep looking up.